Hello. I have a rather long file here. It can be seen that there was a trip and then a wreck losing. This is a 330 kV line with 2 breakers. One of them is under repair. These are voltage channels. That's what I was looking for, a combined signal. Here are tripping signals. Here is the operation of the phase differential protection function. Although if you look at the channels of current and voltage, no disturbances are visible. I will remove all unnecessary channels. Let me remind you that in order to move around the main window you need to hold down Shift and use the mouse wheel. It can be seen that before the trip the combined signal was something about 60 amperes and phase current is 450 amperes. And here the nature of the channel changes, it increases and becomes non-sinusoidal. I will calculate this channel by measured currents. First I will add a positive sequence channel. Now negative sequence channel. Now the combined signal. The value of the coefficient K is 0.12. I'll check if I made the right choice. I'll now leave only the 2 necessary channels with combined signal. There is a difference of almost 30 amps here. But in the calculated channel, the nature of the data does not change. The relay has malfunctioned. Write in the comments what you think is the reason. Now I want to explain why there is a difference in what the relay measures and in the calculation. To do this, I need to show the formula for calculating the components of the negative sequence in complex form. Here A is the rotation operator. So, in order to get the negative sequence, I need to rotate the phase B vector by 240 degrees, the phase C vector by 120 degrees, and add all this to the original phase A vector and divide the sum by 3. A digital device deals with discrete instantaneous values. And here the calculation algorithm is different. Let me explain with the following example. Let the sampling rate be 12 samples per period, then each sample will correspond to a vector rotation sector of 30 degrees. At 120 degrees there will be 4 samples and at 240 degrees there will be 8 samples. Now, to calculate the instantaneous value of the negative sequence, it is enough to add to the current value in phase A the instantaneous value from phase B 8 samples ago and the value from phase C 4 samples ago. Now back to the L60. Let's open the HDR file. As you can see, the comtrade file is recorded with 16 samples per period. Without smoothing, it looks like this. Let me remind you that the device itself operates at a frequency of 64 samples per period. Let's see what happens in these cases. As you can see, it is impossible to accurately execute the described algorithm with such frequencies. This requires that the number of samples per period is divisible by 3. This explains why you can see the negative sequence when calculating in case when there is no asymmetry. Let's look at another comtrade file. Here, a 330 kV line with 2 breakers too. This time both are in operation and there is a short circuit of phase C to ground. Here is the combined signal separately for each breaker. In both cases relays were not very well configured for analysis. It would be more convenient if the sum of 2 breakers was recorded at once. I'll remove everything else. I'll make a sum. Now I will sum the phase currents of both switches and calculate the combined signal from them. I will check whether there is symmetry before fault using the vector diagram. Now I will calculate the positive and negative sequence currents. And a combined channel. I'm removing the unnecessary channels. In this case, the difference is only a few amperes, because the comtrade file is recorded at a frequency of 32 samples per period. Thank you for watching. Peace for everyone.